We have a cylindrical pressure vessel which contains a pressure of 20 MPa, and we have the dimensions of the vessel. We know that the safety factor against sealing must be at least 2. Furthermore, a leak before break criterion must be met, with a safety factor of at least 9 on crack length. In part A, we will discuss if the vessel is safe or not if it is made from 300 M steel, 300 degrees temper. In part B, we will have the same discussion, but this time we will use ASTM A517F steel. In part C, we will determine the minimum fracture toughness, and in part D, we will find the safety factor on K relative to critical stress intensity factor due to the safety factor on crack length requirement. So to begin, we can write the stresses on the vessel first. We will have a sigma x, which is equal to pressure times radius over 2 times thickness. We will have a sigma t, and it will be PR over T. And also we will have a sigma R, and it will be equal to the minus of pressure at inside. And at outside it will be 0. So let's substitute the values first. Sigma x will be equal to 20 MPa times the radius, which is 150 over 2 millimeters, over 2 times 5 millimeters. So that the sigma x becomes 150 MPa. Sigma t is 2 times sigma x, so it is 300 MPa. And finally, sigma r is equal to minus 20 MPa. So let's start with part A. From table 8.1, for 300 M steel, we have the critical stress intensity factor as 65 MPa squared meters and the yield strength as 1740 MPa. We can use the von Mises stress criterion, and we know that according to that criterion, the safety factor will be equal to yield strength over sigma h, and it should be equal or larger than 2. Let's calculate sigma h first. Sigma h will be equal to 1 over square root of 2 times the square root of 300 minus 150 square plus 300 plus 20 square plus 150 plus 20 square. And from this equation we obtain sigma h as 277.3 MPa. So let's check if our requirement is satisfied. The safety factor will be 1740 over 277.3, and it will be 6.3, which is larger than 2, so this requirement is satisfied. But let's check our second requirement. The safety factor on crack length is equal to Cc over T. And we know that Cc will be equal to 1 over pi times the critical stress intensity factor over sigma T square. So it will be 1 over pi times 65 MPa square root of meters over 300 MPa and square of this. So that our XA will be equal to Cc over T, which is 1 over pi times 65 MPa square root meters over 300 MPa square. This is the Cc part, and 1 over T, which is 5 millimeters. And when we compute, we will get 2.99, which is smaller than 9. So this requirement is not satisfied. So we can say that 300 M steel, 300 centigrade temper is not safe. So let's look at ASTM A517F steel. From table 8.1 for ASTM A517F steel, we have the critical stress intensity factor equal to 187 MPa square root meters, and the yield strength is equal to 760 MPa. Again, we know that the safety factor against yielding must be yield strength over sigma h. We know that the yield strength is 760 MPa, and we calculated sigma h in the part A, so it is 277.3 MPa. And we will obtain a safety factor of 2.74, which is larger than 2, so the first requirement is satisfied. Let's look at the second requirement again. And it will be 1 over pi times the critical stress intensity factor over 300 MPa square. This is the Cc part, and over the thickness, so it is 5 millimeters. And we will get 24.73, which is larger than 9. So the second requirement is also satisfied, and we can say that ASTM A517F steel is safe. So we can move to part C. To find the minimum fracture toughness, we will assume that the safety factor on crack length will be exactly 9. So we can say that XA is 9, and it will be equal to, again, Cc over T. This time we don't know the critical stress intensity factor. It is over 300 MPa square and 1 over thickness. So the K1C will be equal to square root of 9 times pi times 5 times 10 to the power of minus 3 times 300 MPa. And this will give the minimum fracture toughness as 112.8 MPa square root meters. And we are also done with this part, so we can move to part D. We know that the safety factor on K relative to the critical stress intensity factor is K1C over K1. We know that the critical stress intensity factor is equal to sigma T times pi times JC. And it is also equal to, as it is given in the question, pi times XA times T. We know that when A is equal to T, leakage occurs. And at this point, the stress intensity factor becomes sigma T times pi times T. So that our safety factor will be sigma T times pi times XA times T over sigma T times pi T, which will give square root of XA, and XA is 9, so that the safety factor on K will be 3.